Given a system of linear equations, there are different ways to find the values of each variable. Check the difference of each method in this video. Welcome to Numerical Solutions to C Problems. There are three equations to solve for the values of x, y, and z in the problem, though it is also in the instruction that instead of solving them algebraically, the use of matrices is to be observed, and also with the iterative methods. For the three equations to be in the form of a matrix, take each coefficient and place them in the augmented matrix, where the bar separates the constants from the coefficients. Let's solve the problem through Gaussian elimination partial pivoting. Recall from the previous videos that Gaussian elimination is a method which ends when the matrix turns into a triangular form, either lower or upper. Then the rest of the solution will be based on substitution. On the other hand, partial pivoting means that the jumbling of the terms will only be done through rows. For this discussion, we will be generating an upper triangular matrix, which means that we will place our pivot element at 1, 1 for a start. Fortunately, element 1, 1 of value 1 is the perfect pivot element. We will use this value to zero out the elements below it. So let's start with column 1. Eliminate 2, 1 using row 1 through the operation thrice of row 1 minus row 2 as the new row 2. For the first elements, we have 3 times 1 minus 3, which is 0. For the second elements, there is thrice of negative 2 minus 5, which gives negative 11. The third elements have thrice of negative 3 minus 2, and that is also negative 11. Then the constants have thrice of negative 4 minus negative 1, which also gives negative 11. Eliminate the third element in the column with the row operation twice of row 1 minus row 3 as the new row 3. The first element is taken from twice of 1 minus 2 as 0. Thrice of negative 2 minus 3 is negative 7 for the second element. The third has twice of negative 3 minus negative 1, which makes negative 5. Then the last element has twice of negative 4 minus negative 7 as negative 1. With the new matrix, we simplify the second row by dividing it by 11. The first element has 0 over negative 11, and that is still 0. The second element is negative 11 divided by negative 11, making 1. The third element is the same as the second. Then the constant is also transformed into 1. Now that all other elements in column 1 are zeroed out, we now focus on the second column. This time, we will use the second row as the pivot row, and 1 is the new pivot element. So with that transform matrix, we aim to zero out element 3, 2, which is now valued as negative 7. Zero this out with the operation 7 times row 2 plus row 3 as the new row 3. The first element is computed as 7 times 0 plus 0, which is still 0. The second is 7 times 1 plus negative 7, which is also 0. The third element is 7 times 1 plus negative 5, and that is 2. Then 7 times 1 plus negative 1, giving 6. Now the transform matrix is in its upper triangular form, signaling the end of the row operations. We now solve for the values of the variables using substitution. But take note that the first column is for x, the second is y, and the third is z. Back substitution would mean that we start the procedure from the end row, going back to the start. So from row 3, there is 2z as equal to 6. By dividing both ends by 2, we have z as 3. Then move to the second row, which has y plus z as equal to 1. This is like y plus 3 as equal to 1, so y is negative 2. Then the first row has x minus 2y minus 3z as equal to negative 4. By substituting the values of y and z, we get x minus twice of negative 2 minus 3 times 3 as equal to negative 4. This is simplified as x minus 5 as equal to negative 4, so x is 1. How about using Gaussian elimination through complete pivoting to solve the problem? In this method, instead of searching for a pivot element equal to 1, we are going to take the highest valued element as the pivot. The pivot element should be placed in the main diagonal starting on element 1, 1. First is to consider the 3-row column elements and identify the highest value, which in this case is 5. The first step is to swap the places of the first and second rows, so the matrix would look like this. When jumbling rows, the arrangement of the variables are still the same. The next step is to swap the first and second columns, making 5 as element 1, 1. Now we are ready to eliminate non-diagonal elements. However, because of our swap, the first column is now y, and the second is x. Now eliminate elements below 1, 1. That is with the operation 2/5 of row 1 plus row 2 as the new row 2. The first element is zeroed out with 2/5 of 5 plus negative 2, which makes 0. The second element has 2/5 of 3 plus 1, and that is 11/5. The third element is solved as 2/5 of 2 plus negative 3, giving negative 11 all over 5. Then last is 2/5 of negative 1 plus negative 4, which is equal to negative 22 over 5. With the new transform matrix, we then zero out element 3, 1, with the operation 3/5 of row 1 minus row 3 for the new row 3. So the first element is 3/5 of 5 minus 3 to give 0. The second element is 3/5 of 3 minus 2, and it is negative 1/5. Next is 3/5 of 2 minus negative 1 as 11/5. Then the last element is from 3/5 of negative 1 minus negative 7, which gives 32/5. After zeroing out the first column, we again determine the pivot element for the second column. This time, the options will only be among the terms in the 2 by 2 remaining elements. From the 4 coefficients, the highest is 11/5, which is coincidentally in the right position. So from the latest matrix transformation, we proceed to zeroing out element 3, 2 using 1/11 of row 2 plus row 3 as the new row 3. The first element is then computed as 1/11 of 0 plus 0, which is still 0. The second element of the new row 3 is 1/11 of 11/5 plus negative 1/5, which is equal to 0. The third element is solved as 1/11 of negative 11/5 plus 11/5, which results to 10/5, or that is 2. The last has 1/11 of negative 22 all over 5 plus 32 all over 5, making 30 upon 5, which is equal to 6. So the newly transformed matrix is the one shown. Since the elements below the main diagonal are already zeroed out, we have a triangular matrix, which means we are ready for back substitution. Start at row 3 and get 2z as equal to 6. Divide everything by 2 and get z as 3. Move up to the second row and don't forget that the arrangement of variables has already been changed. Now we have 11/5 of x minus 11/5 of z as equal to negative 22 over 5. We plug z as 3 and get 11/5 of x minus 11/5 of 3 as equal to negative 22 upon 5. This is simplified as 11/5 of x as equal to 11/5, so x is just 1. With row 1, the equation is 5y plus 3x plus 2z as equal to negative 1. Plug the values for x and z and get 5y plus 3 times 1 plus 2 times 3 as equal to negative 1. This is simplified as 5y plus 9 as equal to negative 1, making 5y is equal to negative 10, and y is negative 2. Same values as from the first method. Now let's solve the system using Gauss-Jordan elimination. Since Gauss-Jordan is just a continuation of Gaussian, we continue zeroing out the rest of the matrix's elements and leave only the main diagonal form. From the upper triangular matrix, we continue eliminating element 1, 2 by using the row operation twice of row 2 plus row 1 as the new row 1. The first element has twice of 0 plus 1, which gives 1. The second is taken as twice of 1 plus negative 2, making it 0. The third is twice of 1 plus negative 3 as equal to negative 1. And the fourth element is twice of 1 plus negative 4 as equal to negative 2. At this point, columns 1 and 2 non-diagonal elements are zeroed out. For the third column, the pivot row to use is row 3, so we can simplify all elements to easily zero out non-diagonal elements. Start eliminating element 2, 3 with the operation R3 minus R2 as the new R2. The first element has 0 minus 0 as equal to 0. The next element is computed as 0 minus 1 as negative 1. The third element has 1 minus 1 as equal to 0. Then the last is 3 minus 1, which is equal to 2. After the last row operation, the matrix transformation is as shown. The remaining non-diagonal element is that from 1, 3. This will be zeroed out as R3 plus R1. The first element is taken from 0 plus 1 as 1. The second element is then 0 plus 0, which is also 0. The third is taken from 1 plus negative 1, which gives 0. Then the last element is then 3 plus negative 2, giving 1. The transformed matrix now looks like this, where there is no need to do substitutions for the values, as from row 1, it shows that x is 1. From row 2, negative y gives 2, so y is negative 2. Then the last, row 3, has z as equal to 3. For iterative methods, the first thing to do is to check if the system can be approximated. Start with the dominant x. With x, 3x, and 2x, the highest is 3x. This should be the first equation. Now check it horizontally with a test that the absolute value of x should be greater than or equal to the absolute value of y plus the absolute value of z. This is like 3 tested with 5 plus 2, where 3 is definitely not greater than or equal to 7. This disqualifies the system to be iterated.